Welcome to the recursion video for Comp 2503. Welcome to the recursion video of Comp 2503. Welcome to the recursion video of Comp 2503. Aha. Now see if by the end of this you can understand the stupid joke that I just made right there. That wasn't an error. That was done on purpose. We are learning about recursion. We are learning about recursion. We are learning about recursion. Okay, but now to actually get into the lecture and stop making stupid jokes. Why are we learning this? This is not really about data structures. This is more of a new programming skill that we will need before we can go into more complex algorithms and data structures. Whereas part of their actual algorithm or part of the, working with the data structure, we need to use what's called recursion. So there are algorithms that employ recursion. We will need to understand it before we go on to learn about trees, tree-based data structures, and other algorithms that use this. So what is recursion? It's more that we often solve a problem by breaking it down into smaller parts. When the smaller problem is identical except for in size, this is called recursion. So being that we may have a bigger problem, but then we can break it down into a smaller chunk and repeatedly keep doing that, that it looks identical to the original problem, but just the size of it is actually smaller. Now this will sound weird, but I got examples coming up that'll make it a little bit clearer. And the idea is that it's a repeated smaller problem. So until the problem with a known solution is reached, we keep breaking it down and then we work our way back up. And it does have some useful nature. So recursion is a programming technique in which a method can call itself to fulfill its purpose. So recursion in general is this breaking it down into smaller parts. Recursion in code, to start with, means is a method calling itself. And then we can start combining these together that, well, we think for a method to solve its task, we could think of, okay, what's the little it's going to do, then how is it going to break down the rest of its actual work into one smaller chunk, which is called one small recursive step. So a recursive definition is one in which uses the words or concepts being defined in the definition itself. You'll see examples coming up. And in some situations, a recursive definition can be an appropriate way to express a concept or problem that could be more. And applying this in programming is a good practice in things you see to be able to solve problems where in general you could use a stack to keep track of things, but recursion using the system stack becomes a whole lot more useful. So here's an example, just stepping back away from code and just thinking of a recursive definition where you get into things what's called a base case and recursive step, is that consider the following list of numbers. So 24, 88, 40, 37. Such a list can be defined recursively, being very generic, is that a list is a number or is a number, comma, then list. And so then the idea is that means it could be list can be recursively back to this could be just a number, or it could be another number and a comma, but it will end with a number at some point in time, or it could only be a single number. So it's a smaller definition, which recursively does steps. Mathematically, you may have seen this before for recursive definitions, so in a formula. So for example, is n factorial from right here, is that for any positive integer n is defined to be the product of all integers between 1 and n. So that's n factorial. So if we have 3 factorial, that means 3 times 2 times 1. This definition can be expressed in the following way, is that 1 factorial equals 1 as a base case, a smaller problem, and n factorial equals just n times by n minus 1 factorial. It's kind of what you expect from here, that if we're doing 5 factorial, that's equivalent to 5 times by 4 factorial, and so forth. And it breaks down to where you finally get to 1 being a base case. So this is what we call a recursive step, where it's the bigger problem, but breaking down to one little chunk of what we're solving here, and then recursing one small step down until we hit a base case from right here. But this is just a smaller definition that you have. Another example that you may or may not have seen is then the Fibonacci sequence, which there's a whole thing about this, breeding rabbits, and more cases of patterns that are seen in nature, like the shell spirals and things like that, is a repeating sequence, and that entire sequence can be defined by this recursive definition here, that we have the base cases. And so what this means is that F0 is the very first Fibonacci number, 0, it's 0. The second Fibonacci is 1, and then any Fibonacci number after that. So if you want the, in this case right now, if we want the third Fibonacci number, so 0, 1, 2, so if it, where n is 2, right here is equal to the Fibonacci number of n minus 1 plus the Fibonacci of n minus 2. So if this was 2 right here, then we'd have f of 2 minus 1, so Fibonacci of 1, which would put 1 here. Then Fibonacci, so n is 2, so 2 minus 2 is 0. So we get Fibonacci number 0, and that's 1 plus 0 is 1. And the idea is this whole sequence is defined by this recursive definition. So what's a bigger, more complex case gets broken down into smaller cases until we hit a smaller base case. So weirder, but we need to get into then recursive programming. Now, I'm not going to go super deep in this course. It takes more practice to learn how to use recursion properly and not inappropriately from right here, but you have to understand at least how to trace it and work with it when it comes to doing some code later on, because it's very useful when we get to complex structures that may have a lot of branching paths, and we need to make a decision of which path to go down. So a method in Java can invoke itself. If set up that way, it's called a recursive method. I'll have examples of this coming up. The code of a recursive method must handle both the base case and the recursive step. So it's got to be one where it doesn't call the method again, but it's just setting up some basic work or returning a basic value. And then you have to have the recursive case where it calls the method again, but then it decreases the size of the problem in some way. So each call sets up a new execution environment with new parameters and new local variables, all that will be stored on the system stack. Similar to what we talked about in the actual stack lecture videos, but there'll be a review coming up. And as always, when the method completes, control returns the method back to where it was invoked, which may be another instance of itself. It's perfectly valid to do. Now, one thing you need to worry about when you're doing recursion is the case of infinite recursion. So this is the same as an infinite loop, where you don't hit the actual ending conditions and the loop never actually exits from here. Is now with infinite recursion, it means it just keeps continuously recursion, which could cause problems like crashing the program later on. So all recursive definitions must have a non-recursive part, so some section where it's going to make a decision and then not call the method again, and then actually and this is called the base case. If they don't, there is no way to terminate the recursive function, and a definition with a non-recursive part causes infinite recursion. So that's the infinite loops. But let's go to some code and let's see some examples of some random recursive methods. So nothing that actually solves any work, it just starts doing some actual recursion, and then show cases of actual infinite recursion. Okay. Switch to here. You've got your example. So first off, we can just make a method in the class. Now, we'll have it do return nothing. We'll just call it run. It'll take in a number right here. Now, what is valid to do is that we've now defined the method up top right here, and so I can call it inside. I could just pass in n. This is valid to do, and this is called recursion. So this is a recursive method. Not done properly. This is very bad just to leave it this way. But the idea is we call this method, then the method calls itself, which then will call itself, which then will call itself, then which will call itself. And the idea keep building up on the system stack. So if I go down to the main, and even just put in 5 right now, we can see what happens. And what you're going to see here is it already crashed, and we got this huge stack dump coming out of here. And the idea is we can keep going back and going back, but it crashed the program, which is this case. Stacks themselves, you can see at the top here it's saying stack overflow. The system stack has a limited size. It can't grow forever. And so if this is pushed too far, like this case that we have this recursive call, that every call is taking up space on the stack, it's going to crash it at some time. So this is an example of that infinite recursion. We need to have a base case where it actually stops at some point in time. And so what we could say is, if num is less than or equal to 0, all right, is greater than or equal to 0, then go into this, and then go -1 just to keep it going down. So the idea is that we'd have these recursive calls. We're going in here, and if the number is greater than 0, then we'll call here, and we'll just decrement it by 1 so the next call goes down. And what we can see we'll just do some print statements, and we will just print out so it shows us where we currently are. So some messages of we're making a call to run, what is the actual parameter, and I'll print it out after. This is going to be interesting to show you again, like we had stacks, that stacks will reverse stuff, is that we'll see the numbers going all the way up as it keeps going in, and then when it comes back for the actual base cases, what's going on. Right here. So now we had 5 here before. I'm going to make this just a little bit smaller so it'll be easier to read. So we're just starting with 3, and we're going to run this. Now here, you can see the output, which seems really weird, but we have to understand what's happening. I can't just look at this method and things like that. We have to understand that there's a system stack that's sitting behind this. And so one is that we have it printing out. We have this case here where it's going up. And the idea is that when the number gets too small, so it's actually negative, it's not going to go into this if, it's just going to go past. And the idea is that's the base case. So I mean, one point in time when it hits that it will not recurse anymore and it will actually stop. And so what you see here printing out here is that we're getting run 3, then 2, then 1, then 0. So you can see that that's its counting down. So it's going here, hitting this method, then calling it again and again and again, each call going onto the stack. We hit the base case, so it actually sees where it goes up here, prints this number out, and then it does not go into recurse and comes to print this out. And we hit here. And all the rest of these are the actual returns back from the method. So we'll come back to this hopefully and like trace it, but I want to go back now to the actual lectures and we can start getting to a review of the actual system stack. So built into all the architecture of the hardware you're working on and the operating systems is that you have what's called a system stack that is used to store all information about the call to a function and a method. So where it's supposed to return to, all the local variables, everything like that is saved onto the stack. And so the idea is that every time a new method is created, it's pushed, idea is that information, what's called an activation record, is pushed onto the stack. You have all the information for its local variables are also added to the actual stack, so pushed on. And every time a function exits, so finishes or returns, then information is popped off the stack, and within there it'll contain the return of where to go to before, which stacks are nice. So examples again, if we come in here, we start with the main. The main is then on the stack. We're then coming in here, we have a call to function 1, which is up here. So function 1 goes on the stack and any data that it actually needs. Next, a call for function 2 goes onto the stack and we're up here. And what we can see is we can see the order that we went. Main to function 1, it's up to here, then to function 2, which went up to here. And the stack kept those previous orders and knows where to return to. So the idea is that when function 2 exits, it's going to return back to function 1 here on this line where function 2 was called from. And then when function 1 returns, it's going to come back down to here to this line where function 1 was called. So if we go in here and function 2 is now going to exit, information is going to be popped off the system stack and it's going to go back to where this specific function 2 was called from, which was right here. And that was the order we had. So it comes back down here and then continues on from there. Now the function 1 is going to exit, so we go back to the actual main. It's going to come back to this line, come down to here now to execute next with function 2, and then you see, okay, we're going to jump now to function 2, so now it's main. And so now this time when function 2 exits from here, it's going to actually return back to the main from here. So the idea is that we have the stack that it keeps building up of that each one of these calls that you have that come from the stack, and as we return, they know where to go back to from their actual calls from the previous steps based upon the ordering of that stack. So definite good use for stacks to preserve the orders of call, to know where to return to in a sequence of calls. So keeping a path. Now, if we were to trace a smaller example like this is a very small, not useful, recursive method. This is just more for demoing, so smaller hello world of recursive ones. This is just one that counts down. So prints the integer out, And if the integer is greater than 1, then it does a recursive step and does it down here. And so this is something you could just write in a loop, but being a recursive definition, we can see one step that's here. We have a recursive step for the smaller ones of just, okay, I'll print out the one integer, the next call will print out the next integer, all the way till we get down to where it's less than 0. And we have a case here at the if that we don't have where it may not go in here, so it'll skip over this and not go into recursive call, and it will actually exit out. If you were to think of the stack and view this here, so the stack of activation records during this execution of the calls, you could view it here if it's 3, and so this was from the main, and we called countdown with 3. Then the first things for main, you'd see countdown of 3 would be thrown on the stack. Then it would be coming down to here and doing the recursive call. Okay, 3 is greater than 0, so go to the recursive call, which means it'll be 2. So we get the next call from here is thrown onto the actual stack. Then the next call is thrown to the stack for 1. Now when we reach being 1, this is not smaller, so it won't go in here, so this leaves off. So the first thing to realize when you're doing this recursive calls, it's printing as it goes down because this is happening here. It will not get to any code below this if until we stop actually recursing, because it won't return back, because it'll keep going up. Once we've hit here for 1, this function will return come off the stack, and we'll come back to this one previously, which is going to return to this line right here and then continue. Then hit here, same thing this will come back on that line and then continue. And so you have to think every time you're calling this recursive call, it's a whole new copy of this actual method is what you can think of. A better way to visually draw this out is like this, is to actually draw it out like boxes where you're doing the calls itself. So you see it here. What I'm going to do is now just switch over to OneNote and draw out this out so you can see what that means. So here, I warn you, sorry for my first horrible case of drawing stuff out, is that to trace recursive calls, I think it's better to, again, to visualize it and draw out the steps. So I'm going to actually draw a box every single time it's for the call. So we're going to assume that we are doing of 3. So the first thing that's going to happen is I will draw one box that's right here. That this box represents that very first call we had. So this is us coming in right here from the actual main. Inside the box, I'll put any local variables or anything I need you to keep track of. But what we know is coming in here first is I have a parameter of 3 is being passed in. So I draw as the first line. When we're coming into here, we have 3. We'll see, okay, well, what will it print out? Over here for the system.out, it's the first line. We have 3 coming into the function. We're right here. So 3 will be printed to the actual screen. Next, we're coming right here to the integer greater than 1. So, okay, that was 3. That's what we have coming here. That is greater than 1, so we will go in and recurse. So the idea here is then it's going to be integer minus 1. So now when we go to do a recursive call, because the same method here, I will then draw another box below this idea and then another arrow saying that we're on the call. And the idea is then when we come back, it's returning this way. So we have 3, there's an integer minus 1, so this is passing in 2. And the idea is we have to remember is that this is the line when we come back, so up here from the recursive call, this is the line where we're going to be coming back to. So now when I have this new box, this is a whole new copy of this function is what I want to think of, or method. And so when we're coming in here, same thing, okay, system.out.println integer, okay, integer this time is 3 is what's, or 2 is what's being passed in. So 2 will be printed to the actual screen. 2 is greater than 1, so we'll do a recursive call again. So I will get another box. And you can kind of see I'm redoing the stack, but I'm keeping track of what step I'm at as we do this. We have integer, which was 2, which was right here, right there, and so that's minus 1, so then we have 1 coming in. And once again, we're at a whole new call to this, so we're coming in to the very beginning. Integer as we printed out is actually 1. We then see is 1 greater than 1? That's no. So it will not go into the recursive call and we exit. We go down here and exit from the function. And so down here for me, this is that last call that we had. So then I'm going to draw a line saying that we're returning back up to here. And so here, this is where we had 2. And remember, it's going to look weird. We're returning back. This is the line where we return from. This is where we did the recursion. So we come back to here. Okay, now we're going to continue on. There's no code below this. So we're leaving from this function here and going up. And once again, we're coming back to this line where it returned from. This is the one where we had 3 originally from here. This is going to leave from here, go to the bottom of the function and exit. So this will then return back to the main and we're done. We're done doing our stop. So this may look weird, but the idea of why I'm drawing these boxes is I can keep track of where I am. Then as I return, I know where I'm going to go back to the recursive line is, okay, I can know what data is coming. And occasionally too, I can also draw if there's a return value that has to come back as well. Okay. Let's go back to here. So it's a way to visualize what you had for the stack, and then to keep track of everything as you're tracing this code. So I do highly suggest to actually do this. Most times I find people just ignore me for this and then lose marks, but this really helps you understand it better. So now let's go on and actually try to write a recursive method in step. So I won't get you guys to do this a lot in the beginning, but it'd be good to know, like, well, if I need to do this, what are we going to do? And I'm going to start with a very simple problem that you could do with a loop instead. But this is going to do with recursion, just easier than to relate of what you understand versus the really complex recursive methods where there's multiple recursive calls are done in the same thing that we'll see later on with larger algorithms. So let's create a simple recursive function that computes the sum of all the integers between 1 and n inclusive, where n is passed in as an integer. We need to determine the recursive step, so how do we break the problem down into smaller steps from right here? And we also need to determine what's the base case, so when do we stop recursing, when will we hit the smallest possible problem we're at. So first thing, let's look at the problem and take some examples. So consider the problem of computing the sum of all integers between 1 and n inclusive. So if n is 5, the sum is 5 plus 4 plus 3 plus 2 plus 1. And here you can kind of see where this starts being like the factorial, where we're breaking it down to smaller problem, that the sum right here, the problem of computing the sum of all digits from here, 5, is the same as going 5 plus 4 being passed in. And the same thing for doing 4 is 4 plus 3 being passed in. So the idea is that each step here is kind of going down by 1. And the smallest we'll ever get to is when we reach to 1. So it's a good case of what we see. So a good base case we start with is the smallest we'll ever get down to is 1. So if we ever get a number as 1, don't recurse, just give back 1. Now recursive step itself is solving 5 is the same as solving for 4, then adding 5 to it. So if n is 5, we could have 5 plus 4 plus 3 plus 2 plus 1, which is 15. But if we have n is 4, that's 4 plus 3 plus 2 plus 1, which is 10. Then add 5 to it, we get 15. And we see, okay, well, this is the same problem, but one's smaller. And so if we just go, okay, take our current number and then add it to a recursive step, breaking it down of n minus 1, we have a recursive step where we're shrinking or getting larger. So generalizing this, solving for n is the same as n plus solving for n minus 1. And n minus 1 is a recursive step. So let's go and actually now code this right now. So we've got the public int sum, int num, and realize here we're also going to have now this where it's returning stuff back. So I'll go to Eclipse. I will now go back to the same where we're working. We had our previous run method, but now here, public int sum, int number. I want to set this up in the beginning. So first, we just have the case of, okay, base case. Start with that in the very beginning, is that if num is less than or equal to 1, and I'm just doing less than so that if somehow a negative number came to this, we also stop from right here. So if it's less than or equal to 1, then just return 1. So that's the answer. So the sum, if we pass in 1, the sum of all digits is just 1. So we return that, but this is a case where we're not doing recursion. Otherwise, else, then we want to actually return back num plus, and then this is the recursive step of sum of num minus 1. And the idea here is that would be that beginning number plus then go and recurse and go in there. So if we want to test this really quickly, we can then call ew.sum, and we can pass in 5, which we should get back 15, which you've seen before is that answer for this. So let's go and run it. And we did get 15. Now, this looks weird here for this case. Now, what we should go back and do to visualize is remembering, well, okay, well, what's going to happen? How can we go about tracing this? So here's another result. In this case, I just used a result variable, and so instead of having multiple returns, but it's the same thing, is we have the non-recursive step, which is the base case. You could have multiple base cases, but it's just basically where you're going to have a path through the code where it doesn't actually have a recursive step. Then here where we have a recursive step here, and that this method's going to be executed before we come back to do any of this work and go back down to here. Now let's go and try to trace this, going back to OneNote again, but doing where sum is 4, so we can see what's happening. Go back down to here. I didn't bring up OneNote. Let's go down here and we'll do this method. So using that same way I suggested for tracing stuff before, we are now doing sum 4. So the very first call coming in from the main would give us 4 as the parameter, and I will draw a box right here to say our method. We have results, that's right here, so I'm just going to put a little r here and equals, and I'm always going to keep track of what result is in there. So we first come in, we're looking, okay, is num equal to 1? Nope, it's 4. So we're going to come down to here and we have result and we have the sum 9 minus 1. So I'm going to circle around here and remember this is the spot where we're going to be returning from, but we have a recursive call. So once again, just draw another box below like this and recurse. And I like to leave them off so it's like a stack and gives us a case where we can like come back up here. But we have our call and it's going to be num minus 1. Num right now is 4, so this will be 3. We come into the method again. Num is still not 1, so it's going to go down to a recursive step again. Right here, so another box. Coming here. Num in the previous case was 3, so this will be 2. Okay, we're still going to then go in. Okay, num isn't equal to 1, so again we're recursing. Like that, from being 1. Now in this case, we are hitting the base case, so it's going to come in here. Num is equal to the 1, so it's going to reset result to 1. 1 right here, and then it's going to return that value coming back up. So we're exiting, we're going to go back up to the previous method, and right here it's going to return 1 coming back up. The idea when we're coming back to where the previous call was, which was right here. And so what's being returned there is what we're seeing down here. So for this call coming back up here where our num was 2, 1 is being returned. And so what you can think here is, okay, from right here, this is the first call. That gets replaced with 1 that was returned from the method call coming down right here, why I drew it. Then we have num. Num is 2 in this case, so that is 2 plus 1. So your result equals 3. And then result is returned. So result gets turned up to here, right here, and result is 3. So I'm putting 3 here. And so these are reasons why I'm doing this, is that as we go down, I'm keeping track of the parameters that are passed in. And as we go back up, I'm keeping track of the returns that we're working with. So now that we've had 3, once again, we're coming back and returning to this line. This time, this one gets replaced with 3. Then we're adding that to num. Num in this case is 3. So this is 3 plus 3 right here. And so that means then that our result is equal to 6. And then result gets returned. So a line going back up, putting 6 there to keep track of it. Once again, we're coming back to where we return where our recursive step was, which is right here. 6 is what was returned, so this gets replaced with 6. Num in this case is 4. here. So we get 4 plus 6, and so result will be 10. And then that's finally what's returned back here is 10. So hopefully you can see what we're working by is that you can see those activation records being called as we're pushing onto the stack and then returning back from the system stack, and why I highly suggest having this as the way that you trace stuff out, doing it on paper instead of trying to do it in your head to make sure that you're understanding recursive calls. If you look in the actual lecture material, there is a bunch of other code examples and tutorial stuff that I suggest you take a look at and practice tracing yourself as well. And you can see the same kind of result that we have here for those returns, but you can draw another way to draw this from your main and drawing each one of your calls, knowing the parameters as you're going down, and then as you return, you can see the steps of where it's going back to trace. This is very good practice because on future stuff I will ask you to trace recursive functions and to show your work, and to do that I expect to see a chart like this, or like the one that I drew in OneNote. Now what becomes a little bit more complex and what's actually useful is that all those previous ones, these were just stuff you could have done with a loop. They're not the real use of why you'd want to use recursion. Where you want it is cases where there's more complex structures and you need to keep track of multiple paths. And to do that, you generally will have multiple recursive calls. So for example, if we were to try implementing, making a function that returned back a specific digit in the Fibonacci sequence, we would actually need to go in and code that, and we could do that here, doing the case of, okay, if n is equal to 1 or n equal to 0, just return n, which is those first two base cases that we had back here. So for the first digit and the second digit, just return back the 0 and 1, which matches here. Otherwise, your new Fibonacci number equals Fibonacci of n minus 1 plus Fibonacci of n minus 2. So you can see that we have two recursive calls here. And so that zigzag stair pattern for tracing won't work anymore here. We need to do this a little bit differently. And here's an example of tracing if this was just 3. So if we have 3 right here and drawing this out, then you come down here, okay, we're not the base cases, then we have n minus 1 plus n minus 2, so you have a call here where it's Fibonacci 2 plus the Fibonacci 1. Then the next calls, and it has to go through doing each of these calls. So it'll always do this one first, then this one. Come back here, we get the Fibonacci 2, then has also got to come in here. Then we're getting 2 minus this, which is 0, like 2 minus 1 is 1, and Fibonacci is 1. So we're getting calls to Fibonacci of 1, Fibonacci of 0. Each of these will be base cases, so they'll return back 1, return back 0. This will be added together 2, which will be returned back up to here and up to here. And what we're getting to is, you're going to see coming up in future lectures, is that this looks like a tree-like structure when it comes to a data structure where you have these branches. And the idea is that, well, only one function at a time can be executed. So it'll be go like da-da-da-da-da, back up to here, down to here, and then back up, and going up here, down, and over. And so this is one way to subdivide the problems where it's going smaller. But also, this is a lot easier to write using recursion than if we had to try writing this using a stack ourselves, which is doable because we'd have to keep pushing and popping all the values off the stack ourselves, or instead we can use the system stack to do this. We will come back to this in the future when we have to deal with trees and what's called tree traversals, for sure. So let's do a smaller manual trace of this, and just doing with Fibonacci 4 now with the actual code. So coming back to what we had here. So I just want to get this code so we have a copy of it. We will now switch to OneNote, go a little further down, and add in the code. So we just have it here. Okay. So this, we're now doing Fibonacci of 4. So the very first call we have here is, let me draw that a little bit better. I want, just be careful for drawing, laying this out can make it easier to see. We're just going to see right here, fib of 4. We come in here that we know we have num, that equals 0 to start with. Now we come to this line. Right here, we're not the base cases, so we're going to come down here and we're going to do this one and then this one. So this will be 1, then this will be 2. So the idea for this one is we have one recursive call going down. So it's going to go do this one first. and that's the n minus 1. So n here is 4. So this will be the fib of 3. That's going to be called. Now fib of 3 will come in. It's going to come down again to this one here. And we're going to get a call to another function, f of 2. It's going to come in here. We're still not at our base cases, so we get one more coming out of this. One. Now when 1 comes in, right now this is one of the base cases, so n is equal to 1 or n equals to 0, where just num will be set to 1. So n equals 1. Does not recur, so it goes down and returns that. So this means that from right here, 1 is returned back up. It's returning to this spot here. So next it's going to go on to do this one, so that's n minus 2. And in this case is 2. So we'll make another call right here going down. And then that's going to give us f of 0, so the 2 minus 2. That is one of our base cases again. That's going to return then coming back up to here, and it's going to return back 0. And then we finally come back up to this function. Both recursive calls have been done, and we know looking at these values here that we've gotten this return back 1, this return back 0. We add those together and we're going to get 1. And so in this case n equals 1, and then that exits out, which then returns back up to the previous call that came here. You can see how this starts getting complex and why I just keep drawing it out. So we get 1 coming up to here. I knew that from this previous call. So in this method we would now be returning back from this call, and it would be giving us back 1 right here. And so now we got to go on to do this call here. Which is 3 minus this, which gives us 1. It's another one of our base cases, so this will return back 1 from right there. So this one returns back, gives us 1. 1 plus 1 equals 2. So n equals 2. So this function then finally returns back up to here, and it returns back 2. And that's the weird thing. So we've gone down more of these ones of why they're to the left, and so this one was to the left, so that's why I keep drawing to the left. This one was to the right, so right here, so I draw that one to the right. So we've come back to this method. This gives us 2, so now we need to go off and do this one. Of 2. Now I'm not going to finish this off because we're going to see a repeated pattern that this is for 2. This is similar to this one that's just down here. It gets more complex. So it's a weird way to draw it out, but this is why I started with the linear ones. It's easier to trace and understand those versus than these ones that are more complex to know the path that it's actually traveling through. But the visualizations help me in actually knowing where was I? What was all the data, not trying to keep that all in my head. Now, if we look at recursion versus iteration, so iteration here meaning just that we're using a loop to step forwards versus using recursion, is just because we can use recursion to solve a problem doesn't mean we should. So for instance, we usually would not use recursion to solve the sum of 1 to n. You would just write a loop to do that, or use a specific mathematical formula. The iterative version is easier to understand. In fact, there is a formula that computes it without a loop at all, and you must be able to determine when a recursion is the correct case to use. So in that case, I used it because you could understand how to do it in a loop, and so it was easier to know with one recursive call to know what was the next step, whereas you saw with Fibonacci, to trace that, it's a little bit more complex with multiple calls and what to do and design them. So first off, if you can do something with just a loop, use a loop. Don't use recursion. But there's going to be cases where a loop doesn't do anymore, like with the Fibonacci sequence, is that you could do that with a loop to set it going forwards, but there's going to be some case for algorithms where a loop would not be a good choice because you would have to use a stack and a loop to solve it versus what we could just write it as simpler code that may be a little bit more complex to understand at the beginning, but it'll make it easier to actually implement. So every recursive solution has a corresponding iterative solution because really we're just using the system stack. And so instead, if we made our own stack and then properly pushed and popped stuff from that stack, we could implement what we saw beforehand. So we would just need to set up a stack to keep track of the actual previous information that we're working on. A recursive solution may be less efficient as well, you need to worry about, and furthermore, recursion has an overhead of all the method invocations. However, for some problems, recursive solutions are often more simple and elegant to express than if you're trying to do them more complexly. So for example, let me try to improv now, and we'll go and implement the Fibonacci sequence as a recursive function, and then see how could we do that then using a stack instead. So first thing, okay, if is equal to 0 or n is equal to turn n, so our base cases. Else return fib 1 n minus 1 plus fib of n minus 2. And so we can now go down to the main and we could set a loop up to print out the couple sequences of the Fibonacci num sequence. So we'll just get to print out the first 5. Well, we'll get to print out the first 6. So you can say that sequence the previous, knowing that these two add to get to 1, 1 plus 1 is 2, 2 plus 2 is 3, 2 plus 3 is 5. So that's working properly here. Now this one can be done with an actual loop. So just to say that this is more of an iterative one, is that I could start from right here. To start with, we'd want the similar thing for the base cases, where we're not recursing before we do anything, that if n is 0 or 1, just return that number. Otherwise, we can then set up a variable to hold what we're currently going to be calculating for numbers. And then we can set up variables to be the previous numbers we start with. So this is just n minus 1 and n minus 2. And setting them up so you can see that they are what you expect in the very beginning. The first numbers, if we just had the two of these together, of n and 1, we're always going to, in the fact that num will always hold the next actual Fibonacci number. So this is the first Fibonacci number and then the second Fibonacci number. Now we want to just keep adding together. So while our n we had here in the beginning is greater than 1, so calculating the rest of the actual digits, we then say, okay, num is equal to your n1 plus n2, so your two previous Fibonacci numbers, right there. We then need to update them, so we know, okay, n1 should be now what is you're supposed to be your next, what m2 was, and n_2 should equal num. So basically we're just moving forward. We're calculating the next actual Fibonacci number, then we're storing, okay, what was the second one into 1 and then the new one, just so that we always have the two previous numbers from right here. Then n minus minus for that countdown. And then finally just return return num. So that is, we're just calculating as we're going. It's like, okay, here's the new Fibonacci number. Okay, then update what are the two previous Fibonacci numbers and keep repeating that process till we've got it done. And go run. And we can see that we had the same sequence we had before, so that recursive. So this is the recursive steps. This is the iterative loop. Now in this case, I'd say, well, we've got the iterative loop. The recursive one is a lot more elegant and smaller code, so I'd probably go with that. You can see how this looks a little bit more as the steps as the actual loops and takes a little bit more. But now let's say if I take this out and we just doing the opposite of now saying, okay, just to show you that any recursive algorithm that we had, so I'll just take all of this out from right here and show that, okay, any recursive algorithm we have like this can also then be done with a stack itself instead of using the system stack. So to start with here, just like the previous examples, even doing it with an actual loop, just have the case if we've hit the base cases, just return the numbers. Otherwise, next we want to set up a stack. So I'll use the stack from the Java collections classes, so java.util. I'll make int num equals 0. Num will always hold the current actual Fibonacci number we're calculating, and in the end we'll hold the final digit where we're going for. We want to set stuff up on the stack in the beginning, so the push 0, so the first Fibonacci number, and s dot push the second Fibonacci number to start stuff off right here. Now, similar to before, while n is greater than 1, we want to keep calculating every single Fibonacci number. So while it's greater than 1, keep going up by 1. And so the first thing we always want to do is that we know the top of the stack will always contain the current Fibonacci number, and then below that will be the previous Fibonacci number. So we can go int n underscore 2, so which would be the current, equals s dot pop. So take that one number off, int n underscore 1, take off the actual previous one that's on here, then num equals n underscore 1 plus n underscore 2. And then now what we want to do is we've taken the stuff off the stack, so we want to put our two previous actual numbers back on the stack. So s dot push, doing the right order, is this is now where we be, okay, this is the second one, and then we want to put on the newest, so that we always have the newest Fibonacci at the top, and the one that's supposed to come before it is from right here. And keep going through those steps. And if we've done this right, we've got a third solution to the same problem. Oops, got one small error. So there you go, we got the same. But once you can see, well, you can done it as a loop. We can do it as a stack in implementation, but just more for elegance, look at this. 2 lines. 2 lines instead of this larger case and more steps for us to deal with it. Then yeah, like I would use recursion instead. So we can get rid of all of that and realize we've got these same steps, but realize there's a lot of overhead on top of it, but it makes for an elegant little solution that we're working with. And this was mainly just to demo the fact that sometimes recursive stuff just could be done iteratively, but there's some cases where you can't. And even in that case, you could write it as an actual, you could actually write it as a stack and iterative case, but the recursion would be a much more elegant, simpler way to actually write it and get to the same problem. So much shorter, but taking advantage of that, we know that we're using the actual system stack. So I think that's enough for today on this topic. I suggest you go and play with this, do more tracing. You don't have to worry about how to write recursive functions perfectly yet, but it's good to understand, to visualize it, that you at least know how the stack is happening and knowing what code is run before recursive call versus when the code will be run after recursive call, especially when you're going up and you're hitting those base cases. So it's from all those cases. So from there, I just want you all to continue being the great people that I know that you are.